just share the slide. It's a real pleasure to be here to speak at Beyond the Edge. I think this is a wonderful initiative, and we need the energy of all these young researchers to face the challenge that are in this field. And I would start from my point of view and state what I believe is the big challenge we can face in the following years. It's not unreasonable to face in the following years. And this is a network theory challenge, which is the challenge of formulating a new theory for complexity and complex networks and higher order networks, which include network topology, geometry, and its interplaying with dynamics, and possibly interpret this interplay in the light of information theory. And I believe that this new challenge, which I stimulate all the young researchers here to address, is really beyond the corner, and we can really make significant progress in this direction. And this theory ultimately will establish a framework to address common question coming from brain research, theoretical physics, and it can help us formulating new algorithm for AI and learning. And in particular, I'm thinking here about possibly formulating unsupervised algorithm for AI. And I believe that this is a mature time to face this challenge, because higher order networks have really allow us to formulate, build the element on top of which I think this theory can be formulated. And I want to be, since it's the first talk here of this seminar series, I want to be introductive, and start with networks. So networks have been studied in network science, in network theory for more than 20 years now, and I believe they form the fundamental structure of interaction of complex system. So this approach, although it wants to embrace the complexity, is in some sense a fundamental approach, because practically, or a reductionist approach, because all the complexity of a complex system is just reduced to the network of their interaction. Yet, this network cannot tell us everything about a complex system, because they are limited to encode only pairwise interaction between the element of this system. And so we need to scale up this analysis and study higher order network. And here, the research has been developing in this last year in an impressive way. And we have gathered information about this higher order interaction in complex system, and also new theoretical methods to encode for the topology and geometry of this data. So an example of a higher order network that will be familiar with a lot of audience is a collaboration network, where you have, for instance, paper between scientists that co-authored by more than 2 scientists, so representing a higher order interaction between the author of the team, which can be represented as an hyperedge or as a simplex. Another important application is in brain research, where you can have higher order interaction, for instance, at the level of brain region, and these 3 brain regions, for instance, they can be correlated pairwise or activated at the same time, forming a higher order interaction or a simplex. So this study of higher order interaction is also attracting a lot of attention in AI. And my book at the start of this field highlight some of the challenge that lies ahead and how higher order networks can really be a representation for the many-body interaction in complex system. From this book, it emerged a point of view that I've been advocating since then, is that the interplay between the network structure and dynamics that has been a central theme in network science is not only mediated by the combinatorial and statistical property, which are of course very important. We know that the degree sequence affect the critical phenomena of epidemic spreading, for instance, leading to what we know, unfortunately, to be the consequence of risk of big pandemic. But when you look at higher order network, since higher order network allow this topological and geometrical representation, you have also that the simplicial topology and the simplicial geometry affect this interplay between structure and dynamics. And of course, you can use that to model dynamics of a network, but you can also use that to infer data from network, and this is the work of AI. So really, I think we are at a mature stage to address this big challenge. It might seem quite challenging to face that, but I think step by step, we can progress toward this goal. And this talk here aim at showing some progress in this direction, specifically highlighting the relation between theoretical physics and network science and AI algorithm. So as I mentioned, I want to be self-consistent, so I just put there some maybe unnecessary definition of what is a simplicial complex and so on, but I hope this is useful for people that want to approach the field. So simplices, a d-dimensional simplex is a set of d+1 node. So a 0 simplex is a node, a 1 simplex is an edge, a 2 simplex is a triangle, and so on. And these simplices describe the higher order interaction in a complex system and are allowing topological and geometrical representation of this system. So each simplex has a face, has some faces, and the faces are simplices formed by a proper subset of the node of the simplex. So if you have a tetrahedra or a 3 simplex, the faces are for node, 6 edges, and 4 triangles. And a simplicial complex is a set of simplices with an additional constraint that they are closed under the inclusion of the faces. So if you have a triangle, for instance, you need to put all the edges and all the nodes. So over the year, we work on higher order network, and at the beginning of the very beginning of the field, we developed to model this simplicial complex model, which actually allow also like hypergraph interpretation, because at the level of their structure or their structure, it is independent if we consider the phases of each simplex or not. And these are as a general framework of emergent hyperbolic geometry, which generalize growing network model to the context of simplicial complex. So it's a very general, you can build a manifold as in the picture or something more general. And then we have configuration model of simplicial complex as well, which generalize configuration model of graph. So these are very useful model if you want to play with, model of control topology in which you want to test your AI algorithm or you want to simulate some dynamics. I want now to enter into some of the questions that comes that we have been working on at the interface with AI. And before we deal with the Dirac operator, I want to mention this problem of representation of the data. So you assume you have a higher order network and you want to represent it mathematically or formally or algorithmically. And then which representation should you use? This simplicial complex, which I mentioned before, or hypergraph that are actually the literature in computer science. So hypergraph I didn't mention before, but are a set of hyperedge, which are the equivalent of simplices, without any constraint. So you don't have this constraint of the inclusion of the face. So if you have a triangle, you might not have all the links incident to this triangle, but only some, okay? And the question is whether your data set, for instance, your collaboration network, is better represented by a hypergraph or a simplicial complex. Let's see a collaboration network, right? So the collaboration network, you have, for instance, here in case C, you have several papers between the author. For instance, you have B, C, and D that have one paper together, but C and D don't have any paper together. Only B and D have 3 papers together, right? So you would represent this as an hypergraph, okay? And then the claim that many computer science mostly says that if you have if you represent this data with the simplicial complex, you might lose information. Okay. Note that hypergraphs do not have this topological interpretation, while simplicial complex have. So what should we do here? Should we give up any topological representation, or should we represent this data in a smart way, right? And of course, the answer will depend on the question that you ask. I'm not saying that there is a rule and you should always apply a rule. Very often, the hypergraph representation will be the best representation that you want. But if you want to do topology, you might also use simplicial complex without losing information. And this is done, if it is possible, if you consider weighted simplicial complex. So the idea is that you will include in your simplicial complex all the faces of all the simplices. So for the triangle here, BDC, you will include BD, BC, CD, and BD, right? So if it's unweighted, you would not know which link is really there and which link is there only because of disclosure condition. But if you assign the weight in a smart way, and in particular, you assign the weight of the link, that is the bare weight, the real number of paper these two authors have together, plus the number of paper of 3 authors that is that they have together, and this is 3 plus 1 equal to 4, then you have a linear transformation on this weight, right? So the weight that you assign to the simplicial complex are given by the bare weight by a linear transformation, and this transformation is invertible. So practically, if you assign weight in this way, or maybe also there are other weight, you can assign weight in such a way that you don't lose information, so that the weight, you can go from a hypergraph to a weighted simplicial complex representation and back without losing information. And this is really nice because it allows topological and geometrical investigation of this hypergraph data. And we wrote the paper in 2022 with Federica Baccini. And this year in the ICML Prize Challenge, a student of Northeastern, I believe, implemented the code and won several prizes in this machine learning conference. So this is a question of why we represent the data with simplicial complex and the power of simplicial complex to represent the data. So now let's move to topology. What is topology? Topology is the study of shape and their invariant. So the invariant are, for instance, the Betti number, and the Betti zero is the number of connected components. So for instance, a point will have a Betti zero equal to 1, and the Betti 1 is the number of one-dimensional cycle, like they are in the circle. But the sphere, for instance, will have a Betti number B2 equal to 1 because it has a two-dimensional cavity, right? And if you look at a network like this fungi network, for instance, you see if you want to, send a message to somebody encoding for this network, you will certainly mention, okay, this is a network that has some holes. So the holes carry a lot of information about the structure of this network. And there are tools in AI, such as persistent homology, that really capture the topology of this network and the cycle structure. But here I don't want to speak about the structure of the network. I want to speak about how topology can help us study the dynamics. And in this approach, you might go beyond the node-centered point of view. You know that in network theory, the node-centered point of view have been dominating until now. So for instance, a node is infected or susceptible or has an opinion, but actually from the topological point of view, also there are also edge signals. So for instance, current or things like that. And you can also attribute a dynamical state to a triangle. Why not? So these topological signals are attracting increasing attention, and in particular also are quite interesting also from AI perspective, because of course you want to reconstruct or solve an AI problem giving data about this topological signal. An example are synaptic signal between the neurons, which unfortunately is still inaccessible now, but also at the level of the brain region. Olaf Sporns has proposed some new technique to calculate edge signal between different brain regions. And you can have also data which are actually a vector field. So for instance, speed of wind at given location on the surface of the Earth. And this vector you can project on a triangulation of the surface of the Earth and treat it as variable associated to the edge. So mathematically speaking, as cochain. And you can have a current at given location in the ocean and so on. So from mathematically speaking, so if you want to characterize the dynamics of a simplicial complex formed by node edges and triangle, you will consider what we call a topological spinor. So a vector including a 0 cochain, a 1 cochain, and a 2 cochain. So these are practically vectors defined on all the nodes, all the edges, and all the triangles, characterizing this topological signal. So, and with this, you can do discrete exterior calculus. So if you have a function defined on the node, you can do the gradient. So chi3 minus chi1, and you can associate it to the edge and so on. But you can also do the divergence. So if you have a function defined on the edge, you can do flux in minus flux out, and you have a function defined on the node, a 0 cochain, that is now the divergence of the signal on the edge. Or you can do the curl. So if you have a signal on the edge, you can do the circulation around a field triangle, and you associate the curl to the triangle, and so on. Of course, this has extension to any dimension. And this operator, operational linear operator, that are encoding what are called boundary matrices, which are rectangular matrices between node and edges and triangle and so on, and they have a beautiful connection with topology and geometry as well, because they describe discrete divergence, discrete gradient, discrete curl, and so on. So you can also, since maybe you don't want to work with a rectangular matrix, there is nothing bad to do that, but you can also contract this boundary operator in order to form a square matrix, which are called Hodge Laplacian. And the Hodge Laplacian describe an higher order diffusion. For instance, the one Hodge Laplacian describes diffusion from edge through edge, passing through node or through triangle. And these Hodge Laplacian have a very interesting relation with topology, because the dimension of their kernel is the n-Betti number. And they obey Hodge decomposition, the signal on the edge obey Hodge decomposition, for instance, in which you can decompose the signal into a rotational component, so going from a source or going back to a sink, the harmonic component around the cycle, a hole, and a curl flow. And with this algebraic topology tool, you can study collective phenomena at the level of topological signal of higher dimension. So we propose the topological synchronization like a Kuramoto-like model with Millan and Joaquin Torre, and we propose a global topological synchronization with Timoteo Carletti and Lorenzo Giambagli. And here the idea is that the dynamics reveals the topology, learn the topology, and learn to sit on the whole of this structure, because the dynamics is reflecting the property, the topological property of the simplicial complex. But here, I don't want to talk about this in detail, but I want to talk about the use of the Hodge Laplacian more from the AI perspective. So, for instance, in signal processing. So, in signal processing, this has been studied on simplices, starting from the work of Barbarossa and Sardelletti in 2020. Before has been studying a lot on graph, and if you want to have a review of graph signal processing, there is the Bronstein article in 2017, which is quite nice. So what is the problem? So you have a signal, let's say a signal on the node or a signal on the edge. And actually, you don't have access to the true signal, but you have access only to a noisy signal, S tilde. So the noisy signal is the true signal plus noise, which is maybe Gaussian ID on each node or a Gaussian ID on each edge. And then the problem is to reconstruct from the noisy signal to reconstruct the true signal. And you do that by considering a loss function, which minimizes the difference between the noisy and the reconstructed signal in the L2 norm, and satisfy, this loss function includes a regularization term. And this regularization term encodes for your assumption on the structure of the true signal. So if you assume that the true signal is, for instance, on the node of the graph is smooth, then you might use a Hodge Laplacian there, or graph Laplacian there. And so this regularization term will be small, so it will not perturb much the eigenvalue that are close, the component of the signal that are aligned to the low eigenvalue of the graph Laplacian or Hodge Laplacian. So how are these low eigenvalue of the graph Laplacian? They're generally smooth. So you can have, so of course, if you are Euclidean, the harmonic eigenvector is constant in time, for instance, or in space, and the low eigenvalue are long wavelength in manifold also you have, some constant harmonic eigenvector, and then the low eigenvalue are smooth, right? And also on graph, phi1 is relatively smooth. So using a regularization term which include a graph Laplacian, which imply that the signal is smooth. On a simplicial complex, using the Hodge Laplacian would imply that the signal that you want to reconstruct is almost harmonic. So you want to reconstruct mostly the signal around the empty hole. So something like this signal here, right? You have some noisy signal, noise-free flow, and then you want to reconstruct, mostly you are concerned about reconstructing the flow around the empty cycle, empty hole. This is nice. I'm a big fan of this approach, and I think it's really nice and beautiful, but there are limitations, and these limitations are the fact that you can treat only node signal and edge signal separately. So the question is, can we jointly process topological signal of different dimension? And you assume that the true signal is close to harmonic, but what about if the true signal is not close to harmonic? Can you do something else? And here the question is, how can we couple topological signal of different dimension together? The first problem. And if we use only the Hodge Laplacian, the Hodge Laplacian go only from n simplices to n simplices. So it doesn't apparently link topological signal of different dimensions. In order to do that, we needed a Dirac operator, and the Dirac operator comes from Dirac legacy, which of course Dirac is the hero exceptional British physicist, which proposed the Dirac equation for the electron. And one of the properties of the Dirac equation is that when you iterate the Dirac equation twice, you have what is called the Klein-Gordon equation, which is this equation, which is practically iterating twice, you get that the second derivative is equal, if this mass is 0, to the Laplacian. So you want something, an operator was, in some sense, was square leads to a Laplacian. And in order to do that, you construct the exterior derivative, and this, if you work on a simplicial complex of node adjacent triangle with this topological spinor, the exterior derivative would do the gradient of the node signal and the curl the edge signal. And the Dirac operator is d plus d star. And then if everything is in L2 norm, it takes this structure. So you have B1, B1 transpose, B2, B2 transpose. And the diagonal term is 0. So why is this interesting? Well, because if you act with the Dirac operator on a topological spinor, you project the signal. So you project the node signal into the edge signal into the node and triangle, and the triangle signal into the edge. So you can allow topological signal of different dimension to crosstalk. So you can allow interaction between signal of different dimension. And it is a Dirac operator because the square root is the square root of the Laplacian. Indeed, if you do this square, you do this matrix multiplication with these blocks, you get the graph Laplacian, the 1 Laplacian, and the 2 Laplacian in the diagonal. Okay? So it is really the square root of the Laplacian, and has this property that d is equal d1 plus d2 if you are from a simplicial complex in two dimensions, where d1 couple only node and edge, d2 couple only edges and triangles. So this leads to this Dirac decomposition, because practically d1 and d2 not only commute, but their product is 0. And this implies that the kernel of one includes the image of the other and vice versa. And therefore, the signal of topological spinor on node, edges, and triangle can be decomposed in a unique way into the image of the one, the image of the two, and the kernel of the. So this is an extension of what is Hodge decomposition there. And the eigenvalue are either non-zero eigenvalue of D1, non-zero eigenvalue of D2, or zero eigenvalue of D, which have the degeneracy that is equal to the sum of the degeneracy of the Hodge Laplacian. So is equal to the Betty 0 plus Betty 1 plus Betty 2. So the eigenvector have the structure that are either eigenvector of D1, eigenvector of D2, or harmonic eigenvector. And this eigenvector, for instance, this eigenvector of D1, they have a very particular structure. So these are the positive eigenvector. These are the associated to positive eigenvalue. These are the eigenvector associated to negative eigenvalue. And you see U1 is the right and V1 is the left singular matrix of singular vector of the boundary operator, and they are related by the symmetry UV, U minus V, which is also called chirality. So these eigenstate are on node and edge, and they couple node and edge, and here couple on node and edge with a different symmetry, and these are the eigenvector of the two, which are on edges and triangle, obey chirality between them, while the harmonic eigenvector can be seen either on the nodes or on the edge or the triangle. So this Dirac operator has been used in theoretical physics. He has some root on some of the work by Kogut and Susskind in the 70s, but was never used in complex systems before, and I was an advocate of its use in complex system. So it can be used in dynamics, so for instance in Dirac synchronization, in Dirac Turing pattern, and in global topological Dirac synchronization. And I have here just few slides because then I want to go back to AI. So in Dirac synchronization, you can have an ordered state that is very complex because it has many minima, and the minima are related to the zero of the Dirac operator, so to the holes and the cycle. And you can use the Dirac operator also for studying Dirac Turing pattern. So this comes because we had a conversation with Lorenzo Giambagli and Lucille Camon in 2021, I believe. And you can have a species on the node and a species on the edge, and then allow diffusion with the Dirac operator or the Hodge Laplacian, and have static Dirac Turing pattern. But then we also work with more with Riccardo Muolo and Timoteo Carletti, because you can also have dynamical Dirac Turing pattern if you allow 3 species. So in this case, you must have 2 species on the node and 1 species on the edge. And then when you use the Dirac operator, you project the signal on the nodes on the edge and the signal on the edge on the node, but they have different structure, so you might need another matrix to reshape, gamma matrix to reshape your Dirac operator, and you end up with this Dirac slash matrix, which projects 2 node signal and 1 edge signal into another topological spinor. And you can formulate with this three-way Dirac operator a dynamical instability. So you start from a homogeneous state and you put the diffusion with the Hodge Laplacian, and you find dynamical Turing pattern. But you can do also the same with the coupling with this Dirac operator, and you see some important effect of this use of the Dirac operator that leads to this kind of seemingly more regular structure, which we characterize dynamically and which we believe it depends on this chirality symmetry of the Dirac operator. But actually, it came to a surprise to us that with the Dirac operator as well, this can lead to Turing pattern. Going back to AI, the question is, so we see that with the Hodge Laplacian, we can treat topological signal of different dimension. Can we use the Dirac of different dimensions separately? Can we use the Dirac operator to jointly process topological signal of different dimensions? So you have, for instance, a true signal on node, edges, and triangle, and then you add some noise, and then you want to reconstruct the signal. And this reconstruction should jointly include node, edges, and triangle signal. And this is work with Lucille Camon and Michael Schaub. So the idea is that you have your topological spinor defined on node, edge, triangle, for instance, and you have a true signal plus noise, so you have only access to the noisy signal. You want to define a loss function, and this loss function will minimize the distance between the noisy and the reconstructed signal and obey some regularization term. And then the regularization term we took is the expectation of D minus E identity square. So if this E is equal to 0, you have D square. This is essentially Hodge Laplacian kernel, and you will process node edges and triangle signal separately. But when E is different from 0, you might jointly process node and edge signal together. So this is the Hodge Laplacian filter in which you don't filter the harmonic eigenvalue, the eigenvalue of zero eigenvalue. And here, when we include E, so we shift this filter, and what we hope to reconstruct is mostly the component of the true signal aligned to an eigenvalue of to an eigenvector associated to eigenvalue, I don't know, 0.5 here, right? So the fact is that, so here we move from a low filter in which we assume like the signal is harmonic, is almost harmonic, to a signal processing that in which we assume, the assumption is that the true signal is an eigenvalue of energy E. And the interesting fact is that E will be learned from the data. So E is not an input of the algorithm, but will be learned from the data. The only assumption is that we make is that the signal will be aligned to an eigenvalue of the Dirac operator. So actually, this is a little bit of a technicality. What we do is we use Dirac decomposition. So we work with signals that are in the image of D1 or D2, so all in node and edges or edges and triangle. And this, as I mentioned, this E is the eigenvalue of the corresponding to the component of the true signal which we don't want to filter, the main component of the noisy signal. And this E can be interpreted as the expectation of the Dirac on the true signal, which allow to interpret the regularization as a minimization of the mean square error of the signal around E. And this can be learned from the data. So before we learn on the data, let's see what happens, if you have a Florentine family network, a network test bench, and the true signal is aligned with an eigenvector of the Dirac operator. And then we consider the signal and the error associated to this reconstruction, which minimize the loss function, right? As a function of the value of E. And if we have E equal to 0, so Hodge Laplacian, we have quite a big error because the eigenvalue E is not the lowest eigenvalue of the operator. But if E matches the real eigenvalue, we can lower the error significantly, right? So here we just sweep over E, we don't learn E. But actually we can learn E. So we do practically assume that we make a guess of E, we minimize the loss function, and then we do practically a gradient descent, and we lower E on the gradient descent according to the gradient descent, and we reiterate. And if we iterate and the noise is not too high, we can infer the true value of E, the true value of the eigenvector of the signal, and so we can learn and lower the error in doing that. So we can do this on this network geometry with flavor, on node, edge, and edge and triangle signal. And we can also do that on real signal coming from current in the shore of Madagascar. And we find a good improvement, but in particular respect to the Laplacian signal processing, but the improvement is less spectacular, right? So what is the problem? The problem is that this assumption, there are two limitations. One is that the Dirac signal processing consider this eigenvector of the Dirac operator, which we mentioned is like the right and the left singular vector of the boundary operator. So assume a given normalization of the node signal and the edge signal. Another limitation is that we assume that the real data is aligned to a single eigenvector of the Dirac operator, while it might be composed by several eigenstates, eigenvector of the Dirac operator. So in order to do that, we need topological Dirac equation. So the topological Dirac equation I now formulated only for node and edge signal. So you have all the node and all the edge, and it is practically mimicking what Dirac was doing in the continuum. So practically you have I, the imaging unit, derivative respect to time of this topological spinor equal the Hamiltonian psi. And this Hamiltonian is Dirac plus m beta, where beta is this matrix of block 1 and -1 in the diagonal. So now you can calculate what are called the eigenstate, which satisfy H psi equal H psi. And this boils down in solving this system of linear system of equation, and you find that the energy eigenvalue follow the relativistic Einstein dispersion relation, which is what Dirac wanted, where lambda instead of the momentum is the eigenvalue of the singular value of the boundary operator B. So here I'm running out of time. I'll be over time, so I don't go into the detail of this derivation, but of course this is just analytical calculation, and you find that this eigenstate of the topological Dirac equation have as a node signal an eigenvalue of the graph Laplacian, and as a edge signal an eigenvalue of the edge Laplacian. And you have here, if you do the square root, you have positive and negative energy state. So there is a symmetry between positive energy state and negative energy state, as we saw for the Dirac operator. But the symmetry is broken for the harmonic eigenvector. So if lambda is equal to 0, we know that the eigenstate associated to the 0 of the boundary operator are of the Dirac operator are localized on the nodes and have the generally given the energy state of energy equal to m are localized on the node and have the generally equal by the Betti number beta 0. The energy state E equal to minus m are localized on the links and have the generally equal to the Betti number beta 1. So we cannot have this symmetry for this harmonic eigenvector. And so this is depicted here. So here you have practically the cumulative density of state for any network. You can do, for instance, for this fungi network, the cumulative density of state of positive eigenvalue, eigenstate, negative eigenstate, and you see that the harmonic eigenstate are not have a different degeneracy here. So this can really lead to new formulation also in theoretical physics, and for instance the definition of a mass of a network of a simplicial complex, and this mass is a topological invariant which depends on the Betti number and depends on the structure of the network. And it might depend also on the geometry, because you can couple the Dirac operator with the geometry, and then this mass might depend on the geometry of the network itself. Going back to the structure of this eigenvector, so the eigenvector of the Dirac equation are either sitting on the node or sitting on the edge, right? And the one sitting on the node have the generality beta 0 and have energy m. The one sitting on the edge have the generality beta 1 and have energy minus m. Then you have the non-harmonic eigenvector, and these were the eigenvector of the Dirac operator, you know, u lambda, v lambda, u lambda minus v lambda. Now, when we introduce this mass term, we can allow for a different normalization of the node and edge signal. So this eigenstate allow for a different normalization. So here you have some coefficient that depends on the mass. So if you change the mass, you change the overall normalization of node and edge signal. And this is what we will use for Dirac equation signal processing, because this was one limitation in the real data set. You might not have, you might have a different normalization of node and edge signal, for instance. So if you want a description, a visualized description of the eigenstate of the Dirac equation, so here you have mass 1.5. This E equal minus 1.5 is defined only on the edge, right? And it will be very degenerate as the cycle of the network. E equal to the mass 1.5 will be homogeneous on all the nodes, constant. And then other energy, different in positive but also negative, will be both on node and edge, right? So you want to practically the Hodge Laplacian signal processing will deal with signal that is harmonic, but we want to reconstruct a true signal that is not harmonic. So that is defined both on node and edge as in this figure. And so this leads me to Dirac equation signal processing. This is last work we have done with Runye Wang and Yu Tian and Pietro Liò. And this generalized Dirac signal processing, because now we put also a term M gamma, where gamma here is defined as beta in the Dirac operator. So we have that, what we have is that we have a signal now defined only on node and edges, and plus noise, so we have only access to the noisy signal. So we want to reconstruct it, and the regularization term, which reflect our assumption on the true signal, is such that is zero if the signal, the reconstructed signal, is aligned to an eigenstate of the Dirac equation. So we allow different normalization, and we allow the signal not to be harmonic, right? So if em equal to 0, we have the Hodge Laplacian kernel. If m equal to 0 and e different to 0, we have the Dirac signal processing. If m different from 0 and e different from 0, here is a typo, we have Dirac equation signal processing. So this energy can be obtained by minimizing the loss function and can be learned from data. And also the mass can be obtained by minimizing the loss with respect to m and can be learned from data. So the algorithm is a bit more complicated. Essentially, we assume to know E and M. We optimize the loss with D and M assumed to be, and then we do the gradient descent on the energy as for Dirac signal processing. And M is sweep over, so we change M in a given range, and then we choose the value of M which minimize, for instance, the loss, but it might minimize also the dispersion relation. So if we want to have some physical criteria to choose M, we can minimize the dispersion relation, the Einstein dispersion relation. So the method is able to reconstruct the true mass and the true energy. And also, if you optimize the mass using the relativistic dispersion relation, the error that you make is still quite low in general, also if the loss is not too high. So also this physics-inspired method to find M works well. You don't have only to minimize the loss function. And so this constitutes an improvement. So we consider first that we compare the Hodge Laplacian signal processing with Dirac signal processing, where the true signal is a eigenvector of the Dirac operator of energy E, and we see that actually the error of Dirac signal processing is much lower than the one of the Hodge Laplacian if the signal is an eigenvector of energy that is different from 0. And then we consider an eigenvector, an eigenstate of the Dirac equation, so with different normalization of node and edges. And also in this case, Dirac equation signal processing now perform much better than Dirac signal processing. So it's even an improvement in that direction. So we checked that this process allows to capture the information on node and edge signal. So because practically you can have different level of error on node and edge, of noise, sorry, of node and edge. And you can see that if when the noise on the edge decreases, you can improve already the error on the node. So, and when the error on the edge signal is reduced, when the noise on the edge signal, on the node signal is decreases. So you can, this method allows you to capture information that goes across the different dimensions. And the second limitation of the Dirac signal processes was the fact that we assume that the signal was aligned to a single eigenstate of the Dirac operator. And then Rooney and Wang, which is a student in my group, came up with the idea to iterate our Dirac signal processing. So practically, you use or Dirac equation signal processing. Practically, you use Dirac equation signal processing. Once you find the most significant eigenstate component aligned to an eigenstate of the topological Dirac equation, you filter out this component and you iterate another time. And you must have a criteria of where to stop. And we choose a coefficient of variation criteria, reaching the expected value. And in this way, here we compare iterated Dirac equation signal processing using the Laplacian or using the dispersion, the relativistic dispersion relation, which needs only 3 iterations to get a very small error. The Hodge Laplacian signal processing is up here. And the iterated Dirac signal processing also is able to decrease here, this is the coefficient of the error, here decrease the error. But of course, it would need more iteration than the Dirac equation, iterated Dirac equation signal processing. So really, by iterating, we can lead to a good performance also on real data. And we applied again to the signal of the current in the shore of Madagascar. And we get a very good, and this is the quantitative data and also visualized data. We get a very good reconstruction respect to the true signal after, here in this case, the second iteration. So here I show you with this Dirac equation signal processing that really you can exploit the tool of topology and physics to formulate new AI algorithm. I want to mention that this Dirac operator can be used also in different other applications. So we use it together with and Kaylin Sear to study molecules, so the structure of a molecule via a kind of Dirac persistent homology. And you can extract different features from this Dirac persistent homology, and in this way clusterize different molecule of different nature with the persistent Dirac quite efficiently. This is for perovskite. And other groups are starting to use the Dirac equation extensively. So one application is for Dirac-based Gaussian kernel, where they use a kernel that is not quadratic in the Dirac operator, but it can allow for a non-integer exponent here. It has been used for a simplicial attention neural network, which exploit Dirac decomposition by the group of Barbarossa. And it was used, actually, the Dirac equation itself was used also for graph neural networks by the group of Frank Hellman. So this is becoming a tool, and I hope you can be interested in applying this operator to AI algorithm or to dynamical process on network as well. As I mentioned, that would be an entire different talk. I mentioned some of the highlights during the presentation, but so I reached my conclusion. So the Dirac operator is key to build a fundamental theory of networks, and it can be used not only for treating topological dynamics of network, but also for a number of applications in AI. And in particular, I told you about this story about signal processing and how the Dirac operator can allow to jointly filter topological signal of different dimension, and also going beyond the hypothesis that the true signal is harmonic, or that the true signal is aligned to a single eigenvector of the Dirac equation or the Dirac operator. So I conclude this talk by thanking all my collaborators. I mentioned them during the talk. My group, Runia Wang, that is here in QML, Federica Baccini, that was visiting PhD student, and Lucille Calmon, now at Sorbonne University, and all my collaborators, which are very enthusiastic and bring a lot of useful idea into the work. So thank you so much for your attention.